environment, conservation, and parks. He received his PhD in chemical engineering here at U of T and in the Southern Ontario Centre for Atmospheric Aerosol Research, with a focus on urban air quality and impacts from vehicle emissions. He is currently working on developing better near-road monitoring of traffic-related air pollutants in the province and improvements of data management and visualization from air quality monitoring networks. Join me in welcoming Dr. Wang.
Today, I'll just be talking about some of the less conventional methods, at least in the ministry, that we're exploring, mainly near-road and on-road monitoring of traffic-related pollutants. So just as a background as to why I care about traffic-related pollutants, 32.8% of Ontarians live within 100 meters of a major roadway or 500 meters of a highway. And in these higher air pollutant regions, adverse health outcomes may be associated with these traffic emissions or exposure to these traffic emissions. And there have been an increasing number of vehicles in Canada over the last 20 years. And with a constantly evolving vehicle fleet, the emissions also change as well. So there is a need for more comprehensive traffic relevant measurements. So the first aspect I'll be talking about is our mobile measurement platform. So the main purpose of this vehicle is to measure facility emissions, but we drive on the highways to these facilities. And what we've done is we've taken advantage of that time on the highway and made continuous measurements during that period as well. So just a brief description of the interior of the truck you just saw. We measure NOx, volatile organic compounds, carbon dioxide, black carbon, PM10, and particle number or ultrafine particles. So this is an average of 16 different trips on the various highways. This is just NO and NO2. There's no point. Well, you can see here there is quite a gradient in the highways. Up here, kind of the Mississauga, Brampton area, you can see it's actually quite high for NO2. And as you move further southwest into Ontario, things get lower. And there's just these high congestion periods you can see here as well by Cambridge and Woodstock, also higher concentrations in red. Moving up. Okay, thanks, Greg. So moving on to black carbon here and particle number. There's less trips to particle number. There's this higher concentration here in black carbon. It's like Kitchener, and that's where we see more trucks. There's also this, it is a lighter blue here, so it's a higher concentration in this entire area. But you move down here around London, there's also high black carbon. So if you compare it to NOx, it is quite a different map from black carbon. And we get these kind of events from particle number. It's usually from individual vehicles that are heavy emitting. So this is quite different from that as well. We also have VOC measurements on this truck using a proton transfer reaction mass spectrometer. So it allows for high resolution measurements of VOCs. And you can see here, you can see that same gradient from Toronto, the GTA area. And here for toluene, that's benzene. Toluene, you can see it much better. So it's high, and then it kind of gets, you see a bit more blue in these areas, but every time you hit a city or area of congestion, you get a bit more of that higher concentration of toluene. Windsor seems to have quite a bit higher toluene, but this is inner city here highway. So I'm going to move on to the next part on how to approach the data and just reporting the concentrations that we see. And one way is to do emission factors. So you can calculate emission factors, which is basically normalization of the pollutants emitted per work done by the vehicle. In our case, by measuring CO2, you can convert that to kilograms of fuel burned. So This is used sometimes in modeling, or you can normally see in like grams per mile for vehicle emissions. But what I like to use emission factors for is to kind of normalize the signal to account for dispersion, dilution. You know, if you're further away from the vehicle or local meteorology, those changes are better accounted for using emission factors. So the rest of the presentation will be talking mainly about emission factors. So we chased some vehicles on our way on the highway. So here's truck number 1. I just picked up a heavier emitting truck. And this is what the time series looks like. On the top is VOC, the particle number, black carbon, PM10, and NOx and CO2. You can see this plume kind of coincides with all the different pollutants, except for maybe the VOCs that are flat. So I'm just going to give you the bars for the emission factors that I calculated from that individual plume. Has no meaning right now, because if you go to truck number 2, that first truck is actually much lower in most of the plumes. So truck number 2 is this fuel transport truck, and we found that for all the pollutants it was actually much higher, significantly higher. Now here's truck number 3, and you can actually see the plume, black carbon coming out of it from the camera. Again, it's even higher than truck number 2. So this is one of the worst vehicles that we saw as we were driving. It's actually in Toronto. But you can see in most cases it's actually much higher. Although the fuel-containing truck had the highest VOC emission factors, the other 2 trucks actually, we didn't even detect anything, and this is most likely because of evaporative non-tailpipe emissions. Now moving on to the second method that we've been exploring in terms of measuring near-road rather than on-road traffic emissions. This is the Highway 401 site. I think you've seen it in some of the previous presentations. So it's 50 meters from the roadway. And similar to the truck, we have a similar suite of measurements here, except for there's an addition of trace metals that we measure in this site. And from 3 years of data, I've been able to calculate emission factors. This is the fleet average distribution of emission factors for NOx, particle number, and black carbon. So if you compare that to the trucks, the fleet emits much cleaner compared to these heavy emitting vehicles. I think that's an obvious point there. I did target these trucks for their emissions. So that's some good news. I wanted to kind of end off around non-tailpipe emissions. So these are from the same site, the highway site in black. And these are trace metal emission factors from the roadway, from the highway. And the other site in red is from College Street at U of T. And you can see for some metals, the highway site is much higher. This is actually for iron, copper, barium, titanium. And a lot of those have to do with brake wear, so it's non-tailpipe. There are some also metals associated with diesel emissions, but some of them are from cross-color road dust suspension. So with the decrease in tailpipe emissions, improving control technologies that are being used, more electric vehicles coming into play, these non-tailpipe emissions, especially for trace metals, are becoming more and more important. So I'd just like to end with a summary. Firstly, a disclaimer that this work is ongoing and all the data is unpublished and preliminary. And our unit, the mobile monitoring platform, appears to be quite suitable for the spatial on-road measurements, and that the calculation of emission factors helps simplify that message, normalizing those measurements of those emissions in both methods of the stationary site and the mobile measurements. It has allowed us to target some of the specific vehicles that are heavier emitters and compare it to the fleet emissions at the highway. And lastly, trace metals are becoming more important with decreasing tailpipe emissions from vehicles. Thank you for listening.